theory part, right? Otherwise, when it comes to X-ray production or photoelectric effect or laser production, those ones, right? You can't just think what's happening there and we can't answer, we can't write, right? So therefore, just go through the respective theory part and get it familiar to yourself and be comfortable, because there are only 2 demonstrations, right? I'm going to make a theory poddai thiyenne me paadame theory poddai thiyenne. Theory poddai nan thiyenne meka manage karan lazy. When we have kind of a small scope of theories, that is easily manageable. That's a benefit. That's a benefit, right? So let's see how this goes. X-ray production. I will recall again how this production goes with the question when we are, as we are moving through, right? Let's see. The figure shows a schematic diagram of X-ray tube. It operates at V 30 kilovolts, and the filament current is 4 milliamperes. Okay. Now, basically, what happens here is, right? I'll quickly explain how this X-ray production happens, right? So what happens is due to this battery, there's a current circulates through this filament. Right? Then a high voltage supply, due to this, a high voltage supply is given between the anode and cathode, right? This is called the anode, that is the target, and this is called the cathode. Cathode is the filament, right? Because of that high voltage supply, electrons which are passing this filament are ejected from the wire and attracted towards this side. And because of the high voltage supply, they gain a massive acceleration, they gain a very high acceleration, and it travels towards this target. And they hit with the target, they collide with the target, they collide on the target, right? As soon as it collides on the target, what happens is its total kinetic energy, right, is immediately lost. Its kinetic energy is immediately lost. When that kinetic energy is lost, right, what happens is heat radiation comes out. Right? When that kinetic energy is lost, heat radiation comes out. With that heat radiation, right, photons which shows the properties of X-rays are also coming out, right? And here, as a ratio, usual ratio is there's 99% of heat and only 1% of X-ray photons, right? So with that ratio it comes out, and that's how X-rays are going to produce. Right? So basically this is what happens in a X-ray tube, right? Basically this is what happens in a X-ray tube, right? So basically this is what happens. Right, now let's get into the question, right? Since this diagram is not clear with these drawings, I'm erasing these drawings. Right. Right. Let's see. Okay. Now, this was a given data. Here, 30 kilowatts. That is important when we are moving on, as we are moving on. Right. Then this is given as 30. This is given as 30. Right. 30 kilowatts. Right. This is given as 30. Right. Then first one. See. First one. Determine the number of electrons n hitting on the target per second. Electron charge is 1.6 into the minus 19, right? So we know, right? We all know current is defined as Q over D, right? Current electricity. In current electricity, current is defined as Q over D. It is also written as Ne over T using charge of an electron, Ne over T, right? Then apply this. Current is given 4 milliamperes, 4 times 10 to the minus 3. I need N over T. Charge of an electron 1.6 10 to the minus 19. Right, then N over T is given by N over T is given by, right? 40 over 16 means 2.5, no? Then 2.5 10 to the power 16. 2.5 10 to the power 16, right? Second one. Calculate the total kinetic energy, K, of all electrons hitting the target per second. Assume that the initial kinetic energy of electrons emitting from the filament is negligible, right? Total kinetic energy from electric fields we know, right? Now the equation is coming from electric fields. From electric fields we know W equals Q delta V, right? W equals Q delta V. W represents kinetic energy. Then kinetic energy is, right, Q delta V. Then from one electron, this is per second, right? Target per second, okay. Then even though that is about energy, so what you are actually going to get is a power. Kinetic energy per second, no? Right. Then for one electron, E, right? Say delta V is delta V. And there are N number of, or N over T number of electrons hitting per second. Then E is 1.6 10 to the minus 19. And delta V, potential difference, was given as 30 kilowatts. Then 30 kilowatt 10 to the power 3. N over T we found as 2.5 10 to the power 16, right? Per second, no? Right. Then simplify this value, right? It is simplified to 120 joules per second. 120 joules per second, right? Or else you can keep this answer as 120 watts. Or else you can give it as 120 watts. 120 watts, right? Third one. Out of the energy calculated in A2 above, 95% of is converted to heat in the target metal. This generated heat is taken out using a copper rod, covered with a spiral copper tube connected to running motor. Right? We call that evacuation. Right? In X-rays, we have discussed on the theories. That is called evacuation. Evacuation process. Right? Evacuation using a rod. Right? Then running motor, calculate the mass rate M in kilograms per minute. In kilograms per minute of flow of water if the temperature increase of water is 57. Take the specific heat capacity of water as 4000, right? 4000, not 4200 now, 4000 now. Okay, then see, now this is connected to thermal. Increase of temperature of water. Then Q equals ms theta. Q equals ms theta. Right? Q equals ms theta. Simple as that. Q equals ms theta. Then if you need this per second, right? Per second, since I have the value of power per second, per second value, even though this is kinetic energy, this is actually energy per second. This is actually energy per second. Then we can divide this both sides by T. Then here power is created. Then power equals I need M over T, right? Then S theta. Apply in the equation. Then power is here 120, but only 95% is utilized. Then 95% of this power. Right, I need M over T. S is 4000, right? 4000. Theta is 57. Right. Simplify. 0 to 0 cancels, right? 12 times 95. And 12 and 4 also cancels, no? Right? We'll simplify this way. By 4 this cancels. This is 4 times 3. Right? 4 times 3. And this is 4 times 1000. Right. Then M over T. is this is 3 times 95 over 57 should be given for a reason, right? This number might be cancelling with 57, we'll see, right? 3 times 95, right, over 10 to the power 4 here, right? 10 to the power 4 here, 10 to the power 4, 10 to the power 4, 57, right? Then what's the value there? Yeah, 3 times 95 is 285. This is 285, right? It cancels off now. 285. that is 10 to the power 4, 57. No? 10 to the power 4, 57. This is exactly 57 times 5. Then this is 5 times 10 to the power minus 4, and this is in kilograms per second now, because I have the value of power here in seconds, but what we need is per minute value, you know. Then convert this to per minute, convert this to per minute. And if this is the per second value, 5 times 10 to the power minus 4 into 60, right, will be per minute, right? Then per minute, 3, no, then that is 3 times 10 to the power minus 3, 3 times, sorry, 10 to the power minus 2, right? 300, then 10 to the power minus 2, that is 0.03 kilograms per minute. 0.03 kilograms per minute. 0.03 kilograms per minute. Right? A normal Q equals MS0 calculation. A normal Q equals MS0 calculation. Right? So I got MOD per second, then convert it to per minute. Right? By multiplying by 60 per minute. Right. Next. Part B. So likewise, when a number like 57, right, that's not the whole number. When something like that is given, right, always you should get an idea that it is given for some reason. So it might be cancelling with a number here, right? Always when you simplify with that idea. Simplify with that idea, right? B1. Calculate the minimum wavelength. Calculate the minimum wavelength, lambda mean of the emitted X-rays. Planck's constant. Planck's constant is given and speed of light is given. Okay, minimum wavelength now. So we know equals hc over lambda, right? Equals hc over lambda. Then equals hc over lambda. And this energy is due to, right? E delta V, right? අපි කලින් equation එක ලියුවා. That is due to E delta V, right? Then energy is E delta V hc over lambda. Simplify. E 1.6 10 to the minus 19. Delta V was 30 kilovolts. 30 kilovolts at 6.6 10 to the minus 34, right? C 3 times 10 to the power 8 over lambda, right? So that's a simplification. Simplify this, right? That is 4.125. 4.125 times 10 to the power minus 11, right? Energy is due to potential difference, right? That equation is coming from our electric fields, right? That is coming from the electric fields, right? And we know energy of a photon is written as h o lambda. Energy of a photon is h o lambda, right? Combine those two, right? So we have lambda, right? This lambda is given as lambda mean for the minimum energy, no? Lambda mean, right? Then part 2. Does the lambda mean value calculated above depend on the target material? Give reasons for your answer. No, because lambda depends on, right? Lambda depends on this energy, right? Lambda depends on energy, right? Energy of photons. To increase energy of photons, what you need to change is potential difference. If you need to increase the energy of photons, have to increase potential difference. Otherwise, nothing with the metal. Check with the equation also, right? And that is no. That's a no, right? So write down minimum wavelength. This is unlike photoelectric. That's why this question is asked, because in photoelectric effect, lambda and frequency depends on the metal, right? But in X-ray, nothing such. Right? Minimum wavelength depends on energy of photons. It varies with potential difference in the language of X-ray, we call this accelerating voltage, right? Potential difference, or in the language of X-ray, that is called accelerating voltage. Accelerating voltage, right? With potential difference, accelerating voltage only, right? So that's a big no. Third one. If the filament current increases, does the lambda mean value calculated above change? Give reasons for your answer. Still no. Still no. Still no. Because, see, what happens is when the current increases, now go to our first calculation. See, when the current increases, the impact of current is to N over D. Impact of current is to N over D. So when current increases, number of photons hitting the target per unit time increases, right? When the current increases, number of photons hitting the target per unit time increases, but yet energy of a photon is unchanged. When current increases, right? There's a impact. There is an impact, right? A special impact and a very important impact on the setup. That is, when current increases, NOD increases. No? NOD means number of photons hitting the target increases. When that increases, X-ray production increases. Higher the number of photons hitting on the target means higher production of X-rays. Production of X-rays increases, but not the energy. Only the production increases. Right? Only the production increases. Then the explanation is, right? Explanation is give reasons. No? Give reason for your answer. Then when current increases, this is explanation. When current increases, only the number of photons collides on target per second increases, right? Right? Now, for your knowledge, you just know that when that increases, what happens is X-ray production increases. Right? X-ray production increases. Only the production increases. But yet, kinetic energy remains unchanged. Because my point is kinetic energy depends only on the potential difference, right? Api equation එකකින් කලින් කියුවා. Kinetic energy depends only on the potential difference. That's the point. Kinetic energy depends only on the potential difference, right? Then 4. The target metals are usually made of tungsten or molybdenum. Molybdenum. What are the reasons for this? Right. Molybdenum is not that popular, but tungsten is popular. Right. About tungsten, we discuss usually in the theories also. Right. Now, what happens here is when electrons are collided, I told you there's a very high heat radiation comes out. Right. Like 99% of heat is 99% of energy is converted to heat, right? So it is its temperature increases rapidly. When the temperature increases rapidly, if the melting points are comparatively smaller values, the anode metal or the target metal will be melted, no? Right? If there are small values, the target metal, anode metal will be melted. Then in such metals that is used in X-ray production, right? Their melting point should be very high. Right? So reason is that melting points of these metals is very high, right? Melting points are high, right? Melting points are high, right? Then Part C. Part C. That's another part. X-ray beam of intensity 5 times 10 to the power 3, Wm minus 2, right? Intensity. Wm minus 2 is incident on a human organ with an effective surface area of 0.01. Calculate the total energy delivered on the organ in 1 second. Total energy in 1 second means, right? Power no. Power equals IA, right? Avi. Me equation we have been using the same equation in the last question also. IA. Now I is given 5 times 10 to the power 3. 5 times 10 to the power 3. And area is 0.01 10 to the power minus 2. Then that is 50 joules. Right? 50 joules. So 50 joules per second. Right? That is asked in 1 second. In 1 second, 50 joules. In 1 second, 50 joules. Right. Second one. If the mass of organ is 0.5 kilograms, calculate the absorbed dose in gray. Right, 1 gray is given as 1 joules per kilogram. 1 joules per kilogram, no, 1 gray. Then here we have 50 joules. See, when you convert, you have to convert this. Right, here you have 50 joules. Right, how many kilograms? 0.5 kilograms. 0.5 kilograms. Then there is 100 joules per kilogram, no? Right, which means 100 joules per kilogram. Then joules per kilogram means 1 gray. Then 100 gray. 100 gray. Right? A normal conversion. Just a conversion. Then third one. Third. What is the best material that can be used to effectively block or shield X-rays? Right. That is an open question. Right. That is an open question. Right. What is the best material that can be used to shield X-rays? Right. Now in the X-ray production tube also, right? So what we are using is tungsten. So tungsten is one. In the X-ray tube also, right? As a shield, we use tungsten. Other than that, right? Concrete is also used, right? Right? Sometimes you might have heard about the nuclear disaster in Chernobyl, right? So in such disasters also, right? In such disasters and other nuclear disasters also, when there are dead bodies are buried, right? When the dead bodies are buried on ground, right? What happens is, what is done is, right? It is covered with a very thick concrete layer, right? That is covered with a very thick concrete layer to minimize that radiation. To minimize the radiation comes out. X-ray is also radioactive, right? Right? So that's used when radioactive samples are buried, right? So concrete is also one. Tungsten, no concrete. And there can be other materials as well. These two are the popular ones. Right? There can be other ones also. 4.1. Why it is important to measure the effective absorbed dose of radiation in sieverts for people working in radiation environment? Right? What is measured in sieverts? Right? We discussed in the theory. Sieverts. In sieverts, health risk of being exposed to radiation is measured. Health risk of being exposed to radiation. That is also called the biological risk or biological impact of radiation. Health risk, right? Biological risk, biological impact, right? The reason is the absorbed dose, right? Absorbed dose can be different, right? From the absorbed dose, right? Or the effective dose. Effective dose and absorbed dose can be different. Absorbed dose is what matters, our biological side or the health side, health impact. Then these two are two different things. That's why that is measured in sieverts separately. That's what you need to explain. Right? What's the question exactly? Why it is important to measure the effective absorbed dose in radiation in sieverts? Right? Working in radiation environment. Right? Then then the effective dose, right? Effective dose and uh, biological dose, biological or impact, biological impact depends on the type of radiation, exposed, right? Now, sometimes effective dose can be same, but with the type of radiation. As an example, say someone has exposed to X-rays and another person has exposed to gamma rays and another person has exposed to alpha rays, right? And another person has exposed to cosmic rays, right? Different types of uh, biological impacts, right? That's why another separate unit is there as keywords to health to measure that health risk or the biological impact. Biological impact is also called the health risk. Huh? Biological impact is also called health risk if you need it, right? That is also called health risk, right? About keywords we discussed in the theory parts, right? Second one, what might be the reason that the effective absorbed dose vary between different types of radiation, even when the absorbed dose is the same, right? So that's what I told you, right? That's what I told you. It depends with the type of radiation, right? To measure it, we have something called Q factor in this radiation industry, right? So Q factor is different. Or you can say Q factor is different, or the biological impact or the biological absorbed dose is different from the type of the radiation, right? What might be the reason for the effective absorbed dose vary between different types of radiation? Then Q factor changes from Q factor depends on Q factor depends on the type of radiation. Q factor depends on the type of radiation. Q factor depends on the type of radiation. Q factor depends on the type of radiation, right? That depends on the type of radiation. So that's what I explained before, right? Exposing to alpha is different from exposing to gamma, right? Exposing to another type of radioactive element is different from exposing to cosmic, right? So likewise, it's different. Part D. Now, when it comes to this question is a little bit lengthier one compared to the previous one we did, right? A little bit lengthier, right? D. When an atom is struck by a high energy electron, an inner electron can be ejected, creating a vacancy in the energy level. An outer electron can transit to the vacancy, emitting a photon with energy equal to the difference between energy levels. This process can generate X-rays with definite frequency. We call this, right? Discuss kara in theories. We call this process of ejecting an electron is linear spectrum of X-rays. Linear spectrum, right? We call this linear spectrum, right? And there was another one called continuous spectrum. This is about linear spectrum, right? So likewise, connect this with the theory. It's this process can generate X-rays with definite frequencies. If the energies of higher and lower levels are E1 and E2 respectively, the frequency f of emitted X-ray photon is given by HF equals E1 minus E2. Equation is also given, right? Energy is given by the difference, right? Then E equals HF. Here H is Planck's constant. First one. For aluminium of E1 equals minus 74 and E2 equals 1624, calculate the energy in electron volts of X-ray photon emitted when electron transmission occurs from higher energy level to low energy level. Right, then delta equals energy kita that is E1 minus E2. E1 is, what about E1? E1 is minus 74. Minus 74. Minus E2 is minus 1624. Right? Then that is 1550 electron volts. 1550 electron volts. Right? Equation එකක් දීලා තියෙන්නේ. Nothing to do. Second one. Determine the corresponding wavelength of X-ray photon produced. Wavelength. Hc is directly given 1240 eV. Right. In electron volts, that is given. Then determine the corresponding wavelength of X-ray. Corresponding wavelength of X-ray. Then the equation was given as HF equals E1 minus E2 is delta E now. Right. So HF is written as HCO lambda. Can be written as HCO lambda. That is delta E. That is delta E. Delta E is known and HC is given. Right. I'm going to plug that value without converting. Then we'll get the lambda also in nano. Right. We'll get lambda also in nanometers. That is given in nano. Right. Then HC is 1240 over lambda equals, this is 1550. All right. So lambda is given by 1550 over 1240. Right. Simplify this. Right. That is exactly 0.8. 155 over 124. No? 155. Sorry, other way around, right? 124 over 155. Right. See, then lambda is 124, 1050, 0 cancels. Then 124 over 155. Yeah, that is simplifiable. That is 0.8. That is 0.8, which means that is 0.8 nanometers, because we plug this value in nanometers. We plug the value of Hc in nanometers. So that is 0.8 nanometers. Right? E. How do hard X-rays and soft X-rays differ from each other in terms of energy, wavelength, and penetrating power? Right. That's a theory question again. Right. We have discussed about two types of X-rays produced in this X-ray tube: hard X-rays and soft X-rays. Right. Hard X-rays are the X-rays with higher energies, higher frequencies. Right. Higher energies, higher frequencies equals HF. No. Higher energy, higher frequency. Then how do hard X-rays and soft X-rays differ from each other? Then energy. About energy, what you need to say is about energy, right? Energy of hard X-rays is higher. Energy of hard X-rays is higher compared to soft X-rays, right? Have to write in words, as a sentence you can write down. I'm just giving you the idea. Then about wavelengths, energy ka frequency ka we know equals HF, right? We know equals HF, no? Then higher energy means higher frequencies. Higher frequencies means lesser wavelengths, because frequency and wavelength is always inverse. Then about wavelengths, the opposite of this. Hard has a smaller wavelength, shorter wavelength than soft, right? Wavelength is opposite because E equals HF. Then, and penetrating power depends on frequency. Yeah, penetrating power depends on frequency. Higher the frequency, higher the penetration. Then penetration, right? Now about frequency we know equals HF. So about frequency we know equals HF. No, about Frequency we know E equals HF. Then higher the frequency, higher the penetration. Higher frequency is for hard X-rays. Then hard is higher, soft is lesser. Right? Penetration depends on frequency. Penetration depends on frequency. Right? Higher penetration, higher frequency. Right. That's it for the second one also. All right. Any questions? Any questions about the second one? Any questions about the second one? Will both black body radiation and X-ray come together or separately in different years? Depends. It depends, right? Sometimes there are questions like from X-rays you are given for like 20 marks and from a radiation part 10 marks, right? Combinations are there. Combinations are there. Combinations are there. Right? Combinations are there. So if you are planning to take this question, right, what my advice is, you have to know all the theories. Right? That's a only small scope here, no? Right? Only a small scope. Taggala make a padam karaganda puluwa. Edi ikkonda padam karagana. And since that is connected, anything and everything connected in matter and radiation, right? And it can be easily connected as well. And the other thing is, it has some connections with lessons like thermal also, right? Q equals ms, Q equals ml wage equations not puluwa. But just about matter and radiation, everything is connected. It's starting from quantum parts for quarks, leptons, nuclear binding energies, nuclear reactions, right? Radioactivity, radiation, black body radiation, then photoelectric, X-ray, right? Everything is connected. Separate rods. As a guessing, what is more prominent to come this year? Just study the last 10 years, right? Just study the last 10 years, right? The idea, right? And there was a pattern before in the questions, right? There have been a pattern in the questions before 2019-20. There was a pattern, but now slowly that pattern is kind of breaking, right? That is actually broken by the professors because otherwise, when students know the pattern exactly, because there has been questions from X-ray and photoelectric year by year for many years in the past, but now those patterns are kind of breaking and they are deviating. So questions are deviating from the pattern. If you study last like 5 years, 6 years, right, we don't have any visible pattern in the questions, right? But easily manageable questions with the things you know. But we can't pinpointly say whether it's X-ray or photoelectric or something like that. Now, since last year has been black bodies, right, and the previous year is X-rays, right? Now, an essay from photoelectric has not been come, then photoelectric and and potential parts are photoelectric, right? Potential parts are photoelectric, right? And nuclear means nuclear binding energy, age determinations, age calculations, right? And other than that, nuclear binding energy calculations, nuclear equations, nuclear fission fusion reactions, right? So those parts are kind of having a potential. And repeating again, anything and everything can be connected easily, right? It can be connected very easily, right? So anything else about the question we discussed before we move on to the next? Anything else? Anything else? So as the next one, I have chosen 2019 because in that one we have a age determination, a nuclear reaction, age determination, right? Those parts, right? In question now it has a potential to come, right? So I selected 19 with some different approach in the 19 one. Right. Any other questions? So is it clear enough? And if you are planning to do this question, right, definitely you have to try the questions in last 10 years. Huh? Try last 10-year past papers, right? Practice them and see the types of questions you have got, right? See the types of questions you have got in last 10 years and get the idea and go to the exam, right? No need to worry. Easily you can write. Easily you can write, right? If you have that idea, right? These are 3 questions out of last 10 in last 10 years, 25, 24, and 19. Practice other questions also. All right. And I couldn't tell you at the beginning. I'll be taking tomorrow for the discussion of Western provincial paper, right? Western provincial paper, right? I'll be discussing Western province paper tomorrow, right? And I'll be finishing the classes tomorrow at like 10 p.m., right? 10:15 so we can start like 11. I didn't share the flyer yet also, right? I will share the flyer. It'll be happening 11 p.m. tomorrow, 11 p.m. onwards, right? 11 p.m. onwards. We'll do the discussion there, right? Western provincial paper, right? So discussions are coming up, right? And you can get all the updates through the channels, right? Check the channel and turn on the notifications and check the channels. And when I put a message to the channels or the groups, right? Check it and you can join on time, right? So I'll be starting at 11 p.m. tomorrow, right? 11 තමයි ගන්න වෙන්නේ ක්ලාස් ඉවර වෙන්නේ 10:15 වගේ වෙනවා, right? ඊට පස්සේ 11 වගේ start කරමු, right? Okay. Western provincial paper, if you have already tried it, you can join the discussion with your doubts, right? If you haven't tried it, I will send you the paper. If you don't have, I will send you the paper. Try the questions and join the discussion, right? 2019.